I'm very pleased and honored to be here. Thanks for the organizers, Sonia and Leo and everyone on the committee. I'm so happy to see my friends like Dietmar and the colleagues that I met in Ohrid. What I don't like is they brought all the secrets from Ohrid. I should have said in Ohrid, whatever happens in Ohrid stays in Ohrid, but I didn't say that. So I will start. Let's see if this is clicking. By saying thank you for Rania also, my fiancée. Her son's birthday today, but she decided to leave her family and her work to be with us. I don't think because you love me, because you love Croatia. She wants to see Croatia. So we heard so much about it. Of course, your hospitality. Thank you so much. And the beauty of the city and the upper city. This is in Zagreb. And I'm very happy. And I want to start my presentation now with the table of contents. I have these chapters from A to F. The first chapter is actually what is ISSMGE, and then some technical stuff from my experience. We'll start with what is the International Society. It's the oldest society representing our profession. It was founded in 1936 by Carl Terzaghi. With 16 countries at the time, they started in the USCA, and now we are 90 country members. As a president, I'm working on making this entire map red. The red countries are the members. Fortunately, Croatia is in red. If you look at Africa, we have a lot of work to do there. And I ask you for your help also if you know geotechnical people in Africa. On our website, you can see how our structure is designed. The 90 country members represent the council, and then you have 12 board members. Unfortunately, Professor Taylor, the Secretary General of the Society, is leaving us this summer. So we just elected a new one, Dr. Andrew McNamara, if you looked at the news. And here I'm presenting the board when I was elected in Sydney. The most recent picture of our board meeting in Egypt. So you see 12 board members and board level committees. You can see them here. Do you have a pointer? So if you look at the circles, these are the board level committees. We have 6 board level committees and 2 projects that if they elaborate, they may become board level committees. You can recognize the board by the pin. And the most important thing with ISSM, the main horse, yes. All right, it's working. So I was talking about the main horse of the society are no, not anymore. So I see this one, okay. You can see them scrolling from the bottom up. We have about 40 technical committees that you can recognize if you visit the website. So these are like subspecialties of geotechnical engineering. And I will explain more in a little bit. Please visit our virtual university. You have about 100 webinars, lectures, especially the young engineers, all with open access for free, videos. And also, if you look at the Journal of Geotechnical Engineering of ISSMGE case histories, there are hundreds of really nice papers you can access for free. Also, I encourage you to open an account with GeoWorld at mygeoworld.com. It's like the Facebook of geotechnical engineers. We talk to each other. And the feature I like the most with ISSMGE, is the interactive map. I discovered in Texas that my neighbor is a geotechnical engineer using this map. You can zoom in, zoom out, and get to know each other as one real international family. For the young engineers and students, also, I encourage you to look at the foundation, and here you can apply and get money to go to the conferences. I encourage you to apply if you want to go, for example, to the conference in Kazakhstan, where we will have a big event, the Asian Regional Conference, and that's where the council will be meeting. Also the awards with ISSMGE, you have the Bright Spark Lecture Awards for the young, and then the Lifetime Achievement Medal. I'll talk about it in a little bit, but first the Bright Spark Lecture Award. This is like the certificate for young engineers who are given the opportunity to speak at the conference. For example, this conference, that's why I was asking to have more students next time. Please note that you can choose 1, 2, or even 3 lecturers from the students, usually towards the end of the conference, and they apply for the BSL award. And so far, in 1 year, we have 17 awardees from around the world. What's new since my election as president? We launched a new phase of the webpage, and this is the Lifetime Achievement Medal. We have so far 16 nominations from around the world. This is a medal that we give to Yurterzagi as a country. So each country will say, hey, I really like this person to win the medal. The person has to be alive, and we're creating another one for those who left us, but the person has to be alive. Priority is given for the old people who can no longer travel. We go to them to give them the medal. So one of these 16, or 2 actually, will win the medal for 2022. Thank you. I come from Beirut, so I was feeling happy. Can you do it one more time? The bomb she was talking about was a little bit louder. Another way to be member of ISSMGE, and here I encourage all those who work with companies. A company can be a silver level, gold member, or platinum member by donating to the society and being part of the CAPG, which is a Corporate Associate Presidential Group, and we have a video I'll show you at the end. And now, my lecture. I don't know how much time I have because it will affect how fast I go. So can you tell me, or because I don't want to take from Carlos' time. Okay, let's go fast. I think I saw something in his pocket. He's from the Italian mafia. I'm worried about that. Look, he has a big bag. I'm worried. No, from the north? Okay. Torino? I love Torino. Let's start. So this lecture is a little bit more philosophical with some injection of theory and telling you about my experience. So you may agree, you may disagree, but I guarantee you will have fun. This is when I was a contractor, so I did it all. Contracting, design, research. To me, geotechnical engineering has to come from different sides and solve different aspects. I will start by Solgi. Solgi is a system I learned to create all the time. You know, in real life, most of the projects are fast track, and the engineer is pressured to give an answer. Give me the design tomorrow. So this is my first recommendation. Don't ever give an answer before Solgi. You collect the data, soil, loads, geometry, and history. One of them may be more important than the other. but you have to collect them all so that they come into your brain before you do any problem solving, especially forensics, since it's the team. And always, always you visit the site in forensics, always. There's so many times I read the data, I go on the plane, I have the solution in my head, I'm thinking about the invoice I'm gonna give. I get to the site, holy schmuck, that's not what I want to do. And I change totally the solution. Think of the mode of failures, which software to use. Because a good suitable solution has to rely on this triangle: safety, cost, and functionality. Even if you're not an engineer, you can build a bridge, but it will cost way more or it will fall. This is good engineering, is when you have equilibrium of these three, and safety should always be priority. And please never ever give an answer without units. Units compatibility, especially if you're in America and use pounds, foot, inches, and then you come here with SI system, and then you go a little bit further, kilogram, centimeter square. You have to always match the units, because 10 milliliters of antibiotics, these are my kids, I was young. 10 milliliters of antibiotics can save your child's life, but 10 liters, we just changed, we removed the M, can kill an elephant. So units, I cannot tell you how many times I go to a failure and the cause deep inside was units. So lesson is, don't use intuition, always go back to theory. If you take the simple, this problem, I take a rope. If I take a rope, I'm sitting on this side and I throw a rope all around the earth and tighten it. And then I make it, and that's the perimeter of the earth, right? I make it 6 meters longer. So from here to the table, I grab the other end and make it looser. And now you have the red line, the red perimeter. The question is, how high will the rope go?
1 meter.
1 meter. But intuition will tell you negligible, right? So if you go to the theory, the simplest theory, 2 pi r, and you discover that not only it's 1 meter, but it's independent of the original radius. So if you have a football or the earth, 6 meters will rise 1 meter. So theory is very important. That's why we marry theory to practice, especially in forensic engineering. And we'll take the simplest action of walking. If you take the simplest action of walking in sand, and we do solging, soil, load, geometry, but also history. Look at the history. You see that the lighter lady has more settlement than the male. So settlement is related to stress. It's not related to the load. This is a proof. So if you take Solgi and use the simplest form of Terzaghis equation, we're simplifying, you get that the ultimate capacity of the load on sand is 1 ton per square meter. But the load from the foot is 3 times that. So is this a failure? If you look at the sand, it depends how you define failure. If failure is, I don't want to see any deformation on the sand, then it is failure. But if it's a building, I am a building, and these are my footing, my feet, footing, I'm standing. So these footings are okay. They settle and they stop. There's no failure. So you go back, well, because it's sand. If you are in clay and soft clay, you may keep sinking. You know the load settlement behavior curve in clay is different than sand. But if you go back and do forensics and say, why did it stop? Let me put more into it. You notice that they're walking in the middle zone, not in the totally saturated under the sea and not in the dry sand. And that gives you some negative suction, which is an apparent cohesion. And if you plug this, you see that it goes way up, and then you have stability because we put 1 centimeter from observation of settlement. So this middle number goes up, and then some cohesion, this first number goes up. So you have an ultimate capacity that's higher than the applied pressure. And now you have stability. And then you say, okay, let me think differently. Why am I showing you this? Because the simplest Terzaghis equation, the most famous in geotechnical engineering, you can use it and reuse it from different angles so you can understand what's happening. And that's what you should do in every single problem you see in engineering, especially forensics. And if you do that, and I ask you, what will happen if you if they moved away from the wet sand into the dry sand? Can you tell me what will happen? And you say, I'll try. So now cohesion is back to 0. And I put the settlement as a variable. And I discover that, oh, they're going to sink 5 centimeters. And that's what happens in real life. And this is how I'm showing you that theory is not to be neglected, no matter how much experience you have. I will move faster. Now, deep foundations. If you bury the person up to the knees or slightly higher, so, SPT in sand around 8, friction about 2 tons per square meter, the pile length 0.6 meter, pile perimeter average 0.3 meters. And the question is, what is the force needed to pull you out of the sand? And here I want to tell you a story. My dad was an engineer, as you mentioned, and he receives a call. This is in 1965, that the trench collapsed. And there's no cell phone, no videos, nothing. He says, okay, wait for me, don't let anybody move. He said, hey, but we have workers under the rubble. We're going to try to save them. He said, okay, I'm coming. One of the excavator operator, his brother was in the trench, and he was buried up to here. So he brought a rope and tied it behind his brother's arms to the backhoe, and he pulled him to save him. That wasn't a good idea, because the force needed to pull this guy out, only right above the knees, the simplest form is about 10 times the weight of the body. And I don't want to tell you what happened, but you can imagine that he died. That's why if you look at the professional rescue people, this is in Boston, of a trench collapse, you can see how they cleared them below the knees before they pulled him out. That's a simple case in forensics. I want to introduce you to equations that changed the world, and 2 equations that changed my life. But first, I need to drink. Break? So, live engineering means check. You can check, for example, atmospheric pressure, if it's 2. You can check centrifugal force, m omega square r. If I go slower, the water will fall. So you keep playing slower and slower until, I don't want to make a mess, but you can use forks to keep your jacket straight. And symmetrical. And you can check actually the 6 equilibrium say you have one finger only to use. You can remove the $100 bill with, because it's an action that is dynamic. Earthquakes, they can do damage more than static load. And if you want to analyze it in forensics, then you say what really happened. So you check the curvature at high speed. So it depends on the speed that will grab the finger and on the friction between the suction wet. And so you can keep going and going, and you can go very far and very deep into the analysis and make it finite element, and then you keep pushing. But my recommendation, simplify it first and then go deeper. Don't start with fluxes. This is a big mistake. Please. One more trick. I'm going to ruin this. Now this one you have to pray. If you are in Croatia, like 11, we pray for Mother Mary. Let's see. One, two. This atmospheric pressure. And now, the suction is holding. So this forensic in everyday life, similar to any problem, how big, no matter how big it is. Carlo, I think I took some of your time. No, I'll go fast. Did you ever taste $100 euro, 100 euro? I will move faster. So these are the two equations, the wave equation, Fourier transform, that changed my life in my PhD. I developed the flexural wave in piles to determine the lateral capacity and integrity of a pile, but this is outside the topic. I'm going to start with 3 case histories, and each, I always like to locate myself geographically, so we are here in Croatia, and I have 2 cases in Nigeria and 1 in Manhattan, New York. The first case, it shows the importance of quality control and monitoring. Unfortunately, I'm going to go fast, but this is a very interesting case. They're building a tower here, and during the excavation, before they even start excavating, while they were drilling, this next door building, an old building, started moving while they were monitoring. And it started moving and jumping, and then the engineer of this building called the city of Manhattan and told them, hey, our building is moving, and the neighbors, I don't know what they're doing, their construction. The city came and closed the project, and it was going to bankruptcy when I was called to that project. So that's where I stepped in and I started analyzing. So we analyzed how in 3D it was moving, and the movement, strain, stress is strain, but strain is stress. So you can tell where is the force coming for this movement to happen, and study the cracks. The direction of the cracks will tell you a lot in forensics. And it was moving at the top here on P8. It moved inward like 96 millimeters, 4 inches or less. So I met with the structural engineers, and he said, well, I felt the deformation is too much. So I said, stop it. This is not a love story to feel. It's engineering. You have to do the analysis. So we conducted the analysis. Look at this solution. The structural engineer, I don't know if they have any structural engineers here, but I'm not saying nice stuff about them, but the structural engineer solved a geotechnical problem by putting struts. I said, what? The building is sinking. You hold it from the top, it's going to crack everywhere. Don't do that. So that was a no-no. I'm glad he listened. And then I superposed And now I'm telling you why, if you're working on a site, somebody is recording site reports. How is the weather? What kind of material came to the site? What happened? This is the site report, right? At the same time, you're monitoring the movements. Why? And I never knew why until I reached here and I asked for all the data. And I put them together because the client said, what's happening? And when I put them together, I was able to say, locate on the dates those jumps. What happened that day? On this day, they were doing secant piles close to the building, big piles. And then on this day, they were hammering sheet piling. And then on this day, down the whole hammer they brought a bigger one. So vibration and remover of material were the cause. I knew what's happening. So if you stop these, you solve the problem, kind of. And then I looked at the design. It was an over-design. Over-design is a problem. Don't think that over-designing is good. It's good for you. It's bad for the neighbors. This is the case here. So, and there is now many conferences. Are we over-designing? And it's on the internet. I don't know if you noticed or have seen this topic. And again, you go to Plaxis, of course. But once you assimilate all the data and you see, you put together, I like what is called matching. So you match what you see, and then you predict what's coming. So we predicted with the strut that the matching of 3.7 lateral will be maximum reach 4.1, so an extra of 1 centimeter. We convinced the city that the maximum, you're not going to see an extra from what happened. Please let us continue. And they let us continue. So I saved the project. I'm not a hero, but I, as an engineer, I'm talking in your name. You know, of course, you have to check the structural integrity, not feel. I'm going to go fast here. And so you put criterion for the tensile strength in the brick construction and the compressive strength, and the previous finite element slides were making sure what is the maximum that before we reach those ultimate stresses in the structure, before you decide about the conclusions. So in the conclusion we said, if this building keeps leaning, we're not going to let it, but even if it keeps leaning up to 8 inches, it will structurally stay in, the integrity is not affected until you go beyond the 7 inches. So that was our conclusion. Structural, geotechnical, you check both in forensics to see which one is a controlling criterion. And then we gave the recommendation, proceed without vibration, make sure the drilling, you use the teach tube method. So the casing goes ahead of the drill head in the big pile rig. So when you're drilling, you don't lose soil from under the building next door. It's called teach tube method in French. So we modified by installing the casing ahead of the drill tool. So lots of money saved, blah, blah, blah. I can see Carlo pushing. No? You're happy? Yes. Okay. So always go back to theory. Never rely on intuition. That's the first case. Second case. Need to drink, but no more tricks. For the second case, is a small bridge in Calabar, in the middle of a jungle in Nigeria. This old road was used. Can we raise the volume? And to place the beams, these beams. Can we raise the volume? The beams were placed before they brought the backfill. When they backfilled, the abutment pushed, touched the beam, kept rotating on the bottom.
That's the story. Then somebody realized that the backfill is too much pressure. They removed it on both ends and attached the beams.
This is an extra addition here. He solved the problem.
The guy that's smart, not smart, is the guy that broke the beams that were on the other side.
So when they called me to this project,
Perfect.
the army was demolishing the bridge because
It's a perfect loading element. If you want to do a load test, we build a tank on top, fill it up with pumps.
Stop.
Do a load
Don't
test
ruin
and
my
then release the
presentation.
water.
He's ruining my presentation. So when they called me, they said, please, the army is removing the bridge because we have a 600-page report from Paris saying that the engineer said you have to demolish the bridge and build a new one. I read those 600 pages. Excellent data collection, soil data, material testing, testing the steel, the concrete, and then the conclusion, demolish the bridge by an engineer sitting in his office in Paris. Whoever came to the site to do all these tests was ignored. Okay, remove the bridge. What is this conclusion? I used 599 pages from this report and just changed from remove the bridge to saying the bridge is safe, use it. Can you believe the difference with visiting the site, reading? I said, no, you're crazy, you're one person. It's a big company in Paris. I said, well, it doesn't matter. Whoever wrote the conclusion did not come see. When I came and I saw some engineer from Canada, they don't even know the name, put those struts in the bottom. So we started analyzing. Okay, this is what happened. This is the bridge in the present situation. And I told the client, this is what's happening. You have the backfill, vertical load pushing laterally on the peat zone, and the piles moved and rotated a little bit, bent a little bit. How do we fix it? We stop the pressure by using empty boxes because they don't have geofoam, if some of you are familiar with geofoam. So we used an empty concrete box, and those stabilizing struts are already in place, and the capacity, we prove it later with load testing. If you don't believe me, we do the load test. If it fails, I give you my PhD degree. If it passes, you give me my money. I saved you $3 million. So that was the deal. Of course, you do the structural analysis of the top, but I'm going to talk geotechnical forensics. So we analyzed that this probably from different data I had, we did matching. So we know this moved 10 centimeters, and we know this moved, so we did matching to detect kind of reverse matching for the soil data, so we can predict, as before, what will happen later. And I love Plaxis. Don't think I don't like Plaxis, but don't jump to Plaxis first. So once we matched the first phase, we did the second phase, and we gave it time for consolidation. You can see it, it's falling. And then you put the load, the traffic load, and look at this. I didn't like this. Even if you put an empty box, I didn't like the solution. And I had no other choice but to put an extra row of piles here. To flatten, ultimately you want to homogenize the deformations. That's the goal. And this in the jungle, this is where the bridge is between two major points, the factory and this is when we did the load test. We put 1.5 times the service load of a truck convoy, and we measured That wasn't the full load. It was halfway. But we measured the deformations with the theodolite, and we predicted that we will stay below the red line, which is the maximum allowable behavior. And with the deformation, we did matching to determine, to predict the maximum movement, and determined K sub S, which is the subgrade modulus of the soil, so we can reuse it for analysis. I'm going fast. Structural analysis in 3D. And then you have to ask yourself, are the piles okay? Because we don't see them, and nobody can dive to go see what's happening. So you do full analysis of the piles with the pile group, and you check the maximum and the average and the maximum moments and shear and all that. And with the existing steel reinforcement in the pile, you check if that pile cracked beyond repair or can still be valid before you do the load test. Actually, we did all that. I'm going fast, but you know all this stuff. AutoCAD. And finally, this is a picture of the execution. So the solution was proven by checking that theoretically, if all possible modes of failure and are passing, and then you do the full loads testing, which is a very important thing. Anytime you, even this roof, and I had this problem in Paris one time, a laboratory asking, can we bring this big machine? I said, it's very simple. Put the same load slowly and test the deflection, you know, L divide by 300 for the span. So you do the same. Full-scale testing is my favorite thing to feel comfortable. Third case. I don't know if we have time. Yeah? So are you enjoying? Because I see silence. Silence may be... Yes, thank you. You know, I don't know if you watch America Got Talent or All the Got Talent. So it's either silence, because everybody is happy, or screaming. Also, it's good. So, but in between, not good. So I was worried. This is a case. This is a crazy case. This is a brand new building. It was the headquarters of a law company, a law firm, attorney, avocat. What do you call them in Croatia? Avocat or law? So, brand new, just finished. Look at this. And it was sinking at a rate 1 millimeter per day on average. Sinking 1 millimeter per day. So it was a race between engineering and life. So when we did the finite element in 3D to do matching, I wanted to see it sinking 1 millimeter per day. Of course, you do Solji. The pile is crossing the 3 layers. They use maximum friction in the medium dense sand and maximum capacity at the end with the firm clay. Good design. So why it's not working? Why is it sinking? If you look, it's not a big building, but very modern. And if you look at the data, this was sinking 1 millimeter per day, 1 millimeter per day, 2 millimeter per day, 3 millimeter per day on this one, small footing. So on the average, the whole building was going down 1 millimeter per day. Differential movements, huge. You see cracks, you can put your hand in it. And it was going. And nobody, I don't know, and then they called Trevi. I'm sure you know who is Trevi, third largest geotechnical contractor. And Trevi immediately started putting micropiles, which is a good thing to do. I mean, you want to stop it. But nobody did the theory behind it to see what, of course, I told them, remove everything from the rooftop. The tanks, the air conditioning, heat pumps, all that, even the tables, the chair, empty the entire building because you are at the edge of failure. When you are at the edge, every single kilogram affects it. Because you're at the edge of failure. It's like you're fishing and you catch a fish and the whole rod is bent. If you put your finger at the butt of the fish, as soon as you touch it, the whole rod will go back up. And that's the same situation. Today we stopped it by adding more micropiles, of course. But the key was, and how did we do it? I started reading the reports, and the biggest word I heard is that the original designer underestimated the load of the building. Structural engineer underestimated. I didn't like it, so I kept reading and reading, checking all the loads per footing, and trying to, visiting the site, trying to see what they're doing, checking the structural integrity of the steel beams that are used to connect the existing footing with the new micropiles, do matching with the load test. They had a load test on the new micropiles. We did curve matching using finite element on the group also and on the single pile. And we saw the difference between the group and the single pile load. There was that's what we call the efficiency, group effect reduction. And we applied all that. Now, if you look at the problem, the load coming from the column on the existing micropile is actually putting more load on the new micropiles because it's sinking. And by the time this is sinking and by the time this has to work and bend, you already expect you need 4 centimeters more of deformation before the new micropile works. I told Trevi, what are you doing? You should, I'm sure many of you already know the answer. I'm going a bit fast. I'm looking at the difference of what is done to what is needed and how many piles they still need. And then I gave my solution. First thing to do is activate the micropile. By activating means you jack it, you push it down. I don't know why this is not working. Yeah. So you push the micropiles down and the building up fast. Every micropile you install, you push it down. And they told me, oh, it's failing. I want it to fail. Take the maximum capacity of that micropile. Quickly, quickly, quickly. And then we start installing micropile and pressuring them. And then I also modified something. It's in the recommendation. I have like 5 points. I'm going fast, but that was the second point. You should come closer to the column. So if you have the footing and the column is my laptop, you come closer, try to come from the corner because they're less steel, so you don't ruin the integrity of the footing. And you put on each corner the micropile very close, and you put the corbel, you inject high pressure to maximize the resistance of the pile, and you activate it. So again, activation close to the column was the solution, or the major part of the solution. And you transfer immediately the load to the building. On global stability, we added about 2 micropiles under each column, but I also created under this, I ruined the entrance of the building, but it's okay, I saved it. Activated. This is the original service load, actual test curve. As the building is sinking, we had to add more piles from about 200 to 240. And then I recommend, this is where the building stopped sinking. And then I had recommended to have at least a factor of 1.2 before opening the building to service again. And then, so this is the extra piles we put. And then I said, connect all the micro piles with a mat as thick as you can. Slowly you add, build it slowly to homogenize and reduce the differential settlements. So after we finished and the building stopped, I couldn't sleep for many days thinking what really happened. What really happened to this building? And guess what I discovered? You're not going to believe it. I discovered that if I give you a number, I say this is a load. I give you a load, I say I want you to give me a pile that will carry this load. Okay, I give you a load, I tell you I want you to give me a pile that will carry this load safely. You multiply that load by 3 and you give me this pile. But if that pile keeps sinking, it means you need 3 times more than this pile. So you die 3 times 3 was an error in units between tons and kilonewtons. It was an incredible phenomenon. I went to the structural engineer, I said, who did the design? And I kept going down the ladder to the youngest engineer in the company. And he said, yeah, I gave in tons. And I said, where is T? The letter T in your design report, I always use tons in Nigeria. And Trevi in Italy always use kilonewton. So they took the numbers without the T. Can you believe this? Brand new building. And they used that kilonewton and designed the micropiles. Look at me, I cannot believe it still now. Final chapter. So that's another thing from my experience. I want you to be one of those here, make things happen. And to do that, you have to be ready to work internationally. You cannot work in Croatia alone and study here and work here alone. You have to be ready. You can, but you have to be ready to work in Canada and anywhere in hot weather or cold weather. But also be ready for the corruption map. I think you are like Lebanon. We are here very red. So yeah, I'm not worried about this. So you are ready for international work. Adam, you're yellow, so you're very good. You cannot work here, man. Everything is under the table. I can work here. If you want to take a snapshot of this, these are my conclusions. So always collect the data. Carlo, I'm finishing, you can see. Always collect the data. Never rely on intuition. Always do the theory. Simplify it if you can, so you get the level of, you estimate the level of the intensity. Don't limit yourself to the code. Codes are made for not so bright engineers. And codes are made so that you don't make big mistakes. But if you can calculate it and innovate, don't limit yourself to the code. Whoever wrote the code may not be as smart as you, especially for this specific forensic project. Codes are not made for failures. So if you are in a failure, you have to think beyond the code. Of course, conduct monitoring and use that observation for matching. And even long term, you contact the client, say, send me pictures of your project, stay in touch with the project. It teaches you more for long term stuff. And be ready internationally, as I said, and connect with me on LinkedIn with your ISS MGE international family. Finally, one last equation. It's the geotechnical fundamental equation. What does it say? It says that to understand soil better, you have to dig deep. To understand love better, Rania, you're not following. You're not digging. You have to dig deep. So, that's the equation. Soil equal love. And this is what Steve Jobs, before he died, said actually in one of his speeches at Stanford University. The only way to do great work is to love what you do. So I hope you love what you do. Thank you very much. I have a 2-minute video. I don't know if we have time for 2 more minutes. Carlo? No, what are you doing? I thought he's getting his handgun. Let's play that video.
We have learned to understand the earth and to use this knowledge for the benefit of all humanity. We create the history underground that makes our planet a better place. We unravel the secrets of the soil and provide foundations for infrastructure that improves our lives and for buildings that connect us, elevate us, inspire us. Geotechnical engineering is our passion. It motivates us every day to face the new challenges of the world in which we live, of the world we are building. The ISS MGE invites you to join as a corporate associate and become a part of a vibrant, dedicated family that shares the passion for charting new paths in our industry. You will be a member of our great geotechnical community, made up of corporations, consultants, contractors, research institutions, equipment suppliers, and product manufacturers, all committed to implementing new knowledge and innovative methods of construction in geotechnical engineering practice. Through your investment, you will support our many educational and research initiatives, such as the Young Geotechnical Engineers Conferences, technology transfer programs, and lecture tours. As a corporate associate, you can contribute an industry perspective to our regional and international conferences and assist in bridging the gap between research and practice. These conferences provide a unique platform for addressing relevant topics in our profession, as well as prestigious opportunities for networking with leading experts and companies from around the world. ISS MGE will be honored if you join as a corporate associate of the oldest and largest society representing our profession. A society that was founded in 1936 by the father of modern geotechnical engineering, Carl Terzaghi, and which today brings together more than 90 countries and 30,000 engineers worldwide. Become one of the companies who are shaping the future of the entire construction industry and be at the forefront of geotechnical solutions and innovations for a safer and cleaner planet.
Let's make our mark on the world. If you love geotechnical engineering, join your international family, and you will love it more.
International Society for Soil Mechanics and Geotechnical Engineering.